Hello! I know I haven't posted publicly in a while, but I'm ready to give it a go again, and I have some exciting news to share with you. I went to England and I did my master's in mathematics. I get to graduate in just under a month. And what do you think I focused on? I focused on Mersenne numbers because they're so interesting. While I was over there, I came up with a new intuitive way to look at Fermat's little theorem. So I hope you enjoy. If you already knew about this, then enjoy anyway. Here is Fermat's little theorem as expressed through circles and stars. Here is Fermat's little theorem in math speak, with these conditions. Let a and p both be natural numbers where p is prime, and the greatest common divisor of a and p is 1, so they don't share any common factors other than 1. Then that number a multiplied by itself p minus 1 times is congruent to 1 in the modular arithmetic mod p. So now we can see an example of this where a is 2 and p is 11, because that's what we were just working with, and we may as well use it for consistency. Now, to show that this is true for the case where a is 2, we're going to look at multiples of 2 when we put them around in a circle like this. First of all, multiples of 2, if we take our regular number line, where this is 0, 1, 2, 3, regular counting numbers. We can see the multiples of 2 by starting at 0 and adding 2 to itself over and over again. What we did before with string art was we multiplied by 2 at every step. Now we're adding by 2 at every step. Wrapped around the circle, we take this and we get this result. We have reached every dot before coming back to the beginning, very much like a spirograph. So every one of these is a multiple of 2 in some way. Here we can see in mod 11, every one of our natural numbers has just permutated around into a different position. Every one of them is still represented. And so what we can do now is we can make an equation where we multiply all of them together. That is going to be the same as multiplying all of them together and multiplying each one of those instances by 2. Now, we're going to leave out 0, because if we multiply something by 0, that's not going to tell us much. So we're just going to consider all of the rest. And how many of them are there? There's p minus 1. Here's what we get for our equation. We get 2 times each instance of a dot up to 10, not 11, is congruent to multiplying each of those numbers by themselves, just themselves, without a 2 every time. Then that is congruent to 2 multiplied by itself 10 times 10 factorial. That is congruent to 10 factorial, all in mod 11. And now we can cancel out the 10 factorial to get 2 to the power of p minus 1 is congruent to 1 in mod p. There's our example. Now, this is true for any p up here and any a in here. We'll just keep 11 because it's drawn already, but let's use a different A just to see what happens. What if A was 5? Then we're skip counting and finding multiples of 5, and so on. And it looks like this, from 0 to 5, and then keep on adding 5. Again, all of the numbers permutate. We get a beautiful star. Each of the dots is reached exactly once, and that's why this is true for every case, for any A, for any P, as long as they don't share any common factors.